Now that we have a pretty good basis for understanding where much of the power of NMR spectroscopy comes from, its extraordinarily high resolution, and the perils of NMR come from the very weak signals that we are actually measuring here. And now we're talking about ways we do our experiments to try to maximize the benefits and minimize the problems. We've already talked about locking and shimming, a way to guarantee that our magnetic fields are homogeneous, and therefore the spectra resolution is as high as possible. Now we're going to talk about a little bit how we actually obtain the spectra and some of the fancy mathematical tricks we use to try to minimize the problems we get from such weak signals. There are actually two ways that you could obtain NMR spectra. One of them, the early one, the older method, is called continuous wave NMR. It's not done that way anymore, but it is instructive to get a feel for how it worked. And the best analogy for it I could come up with for you is simply this. Let's imagine that you're now in a new location, one you're not familiar with, and you're interested in knowing where some of the FM radio stations are in that area. I know these days you could simply Google that information and probably wouldn't really care because you're on satellite radio or some other medium instead. But let's, take it back a couple of decades when FM radio is going to be the thing. And you're interested in finding out what are the radio stations between, say, 96 and 104 megahertz on the FM band. Now, one way you could simply do this and kind of make a record of it is to turn on a classic old radio at 96 megahertz, 96 FM, and draw a line on a piece of paper or something representing how much of a radio station, how strong of a signal you're getting. It would be a low line if there's not much there, just a little bit of static. And if you come to a strong radio station, you're going to draw a line that moves up. If it's a modest radio station, it goes up a little ways. If it's a strong radio station, it goes up a lot. It'll actually kind of resemble a spectrum. Now, what we're going to do is actually, carry out a crude demonstration of that process using a classic Stone Age FM radio. This dates back from the era, when tablets were made out of stone and Zaxby's sold pterodactyl wings, but it comes from, things I've done in my past. And so when we're doing this demonstration, I'm going to essentially just be turning on a radio and making a mark representing the strength of the signals that I'm measuring. Anytime you see, what seems to resemble some schmuck's hands drawing the line or turning the radio dial, just remember that's an artifact of the experimental method that we're doing, and you can safely ignore that. So here goes.
So this tech company called Acrovert is working with...
Better, the truck people. Wow, and what a fantastic ride.
There, that gets us our nice pretty spectrum. But the problem with it is it took us a fair amount of time. And let's face it, if I wanted to do this more finely, I would have taken more time to do it. I would have turned the dial much more slowly and gotten my drawings much more accurately done. Doing a continuous wave spectrum this way takes a considerable amount of time, and the greater resolution you want, the more time it's going to take. But realize one thing, all of the information that spectrum contains, what frequencies the radio stations are located at, and how strong they are, is essentially a spectrum. It has integration-like information and the frequency information built into it. We could extract, in theory, or get exactly that same information by listening to all of the possible radio stations all at once. Imagine, if you will, you could make that radio play everything between 96 and 104 megahertz. It would sound something like this, which admittedly is not all that pleasant to listen to, but contained within that pile of sounds, that seeming mishmash of stuff, is all of that information. What we need to look for there then is there a way to take that really quickly obtained pile of noise and extract out of it the spectral information? And that's where some really fancy mathematics called the Fourier Transform come into this game. So to introduce Fourier transforms, ultimately, I'm first going to play with a tuning fork. Now in front of me here I have a microphone that I've attached to one of the lab probes from Vernier. One of those things you probably used back there in Gen Chem to be a temperature probe, pH probe, and all the other functions that it had. It also does sound, and what I'm going to show you is the sound waves that this thing captures from things like a tuning fork and a few other items like that. So first what I need to do is to sound the tuning fork and then hold it up to the microphone. Now you yourself will probably not hear anything from the tuning fork. They're not terribly loud, but you'll see on screen the wave pattern that the tuning fork makes as it's being recorded by the probe. So here we go. And you can kind of see that interesting wave pattern that it makes. And so if I do the same sort of thing but with a different tuning fork, this one has a higher pitch. I just want you to see what the difference in the appearance of the wave. Anything for my class. There. Now the real fun of this process comes along not when you're looking at one tuning fork, but when you're looking at a complex combination of sounds, something like a radio playing all the stations at once, something like that. But anyway, what I'm going to do is sound both tuning forks and hold them both up to the microphone at the same time. And I want you to see how the wave pattern is considerably more complex when you have two of these being added together. So here goes. Oh! There. Now, the ultimate of this, of course, is a really complex set of waves and sounds that are all mashed together. And so to show that, you are in the enviable position of being able to listen to me sing a note. So here we go. This is what my voice looks like when all the different sounds are analyzed and put on display. La la la, la la la. I know, I should stick to my day job, and I probably will. Now, you've seen the probe here capture the sound waves, but now I want to introduce you to one other aspect of this, how to get out of these sound waves, particularly the complex sound waves. What are the frequencies of sound in those sound waves? That is what a Fourier transform does. I'm going to show that to you, introduce you to the equation, and then show you how it works. First, a quick look at the equation for the Fourier transform. It's a pretty fearsome thing, and no, we are not going to do anything more than what our dear friends in the math department and the computer science department have built into the software we make use of when we do this game. But what I want you to see from this is the following. It basically takes a function that is oscillating over time, like, for example, a sound wave that has been recorded from my voice or from a tuning fork or a bunch of radio stations all playing at the same time, for example. And it takes that what's called time domain oscillating function and comes back with a frequency domain function, it's called. Basically a function that marks, okay, what frequencies went into building that sound wave. Now that's easy enough to say, but it's still a little bit of a fuzzy concept. So let me show you again, using my friend the microphone here and the software, a little bit about how this works. So once again, the tuning fork. Now this time around I'm going to sound it and hold it up to the microphone so it can pick up the time domain function, listen to the oscillations over time. But what I'm going to ask it to do now is to then apply a Fourier transform. And what it will do is come back with, here is the frequency that that sound wave was built from. So here we go. Now what I want you to see is that time domain function oscillating came back with a frequency, and the tuning fork I just used was says to has a frequency of 330 hertz. Okay, it sounds an E note, and that's what the Fourier transform, and here's what the Fourier transform came back with. And so what it did is it listened to the oscillations and essentially came back with, okay, here's a function that marks that frequency. Now the power of this technique isn't with one tuning fork, it's with more complex waves, like you would get if you sounded two tuning forks at the same time. Watch this one. Now, let the system sample the complex wave. You see the wave is has that complex pattern to it. The Fourier transform picks out the fact that that sound was built from a tuning fork at 330 hertz and a tuning fork at 494 hertz. Rather remarkable how that works. And so as the last example of this, once again, the golden tones. Here are the frequencies that make up my singing voice. La la la. No, it's not one of the stellar singing voices, probably because it has quite a complex pile of frequencies in there. But that is how the Fourier transform gets used. So imagine this. We have that complex pile of sounds from the radio station where it's sounding everything from the 96 to 104 megahertz, like we were talking about a moment ago. I said all of the information of that sound spectrum, that FM sound spectrum, was in there, and this is how we would get it. We would take that complex pile of sounds, all oscillating at their own frequencies over time. We would run them through, mathematically, a Fourier transform. And what would pop out is our FM radio sound spectrum. And I want you to notice that was done quickly. We didn't have to sit there and tune it carefully and draw the response or something. We just simply turn it on, listen, turn it off, calculate it. That is one of the major breakthroughs, was the computer power available to do this with NMR, and because it unlocks a lot of the or gives us a great ability to overcome some of the major problems in NMR spectroscopy. Remember, one of the great problems in NMR is simply the signals are very weak. We see very few nuclei actually undergo the transition every time we put the sample in there. And so we are always fighting concentration problems. One of the ways we overcome it is doing this Fourier transform game. What we do is we put our sample in there, we shine our radio frequencies in, we see which frequencies got absorbed. We do that fairly quickly. Then we wait and do it again, and again, and again, and again. We do this several times. The idea is this: if you have really weak signals in there, and let's face it, this is NMR, we do have weak signals, then every time you do this process, the real signals will grow in strength, but any random noise, like the static in the background of a radio, will tend to cancel out. And so it will leave us with a fairly strong signals and all the high resolution we expect out of NMR. And so this was the key breakthrough, not only in proton NMR. Since it was sensitive, you could do that one continuous wave fairly readily if you had very high concentration samples. But this is the technique that broke open carbon-13 NMR. Remember, carbon-13 is a much less sensitive nucleus. The abundance problem is a real crisis there. It was not possible unless you had isotopically enhanced samples to do much with C13 in the good old days. Once the Fourier Transform technique came about and the computer power necessary to pull that off, then suddenly carbon became a routine component of NMR, and the power of the technique really exploded from there. And so finally, I want to show you a couple of details of how we process the NMR spectra. Because what the instrument measures is not really what you see as an NMR spectrum. What it's measuring is a collection of oscillating frequencies. Now, much like the tuning fork here, when I sound the tuning fork, I hear the sound, but over time, I get, the sound diminishes as the tuning fork finally goes silent. It's essentially, I induced it to do a sound, but that sound is decaying over time. In NMR, what we do is we measure what's technically called a FID, a free induction decay, an FID. We put our molecules in the big honkin' magnetic field. We then hit them with our radio frequency energies. We listen to which frequencies are resonating in there, which ones are causing spin state transitions to occur. We listen for those frequencies. That sound, those set of frequencies, is loud initially, we hear it initially, and then it decreases over time. It decays. The induced frequencies decay fairly quickly. And so we listen to the FID, it decays, and then we do it again and add the two results together. Do it again, add that result in, do it again, add that result in, and keep doing this a number of cycles until we get a set of raw data, the FID, that contains all the spectral information. It's much like that pile of radio frequencies, that pile of radio stations. It's a mess to look at. Here's what it looks like. This is an actual free induction decay. It's a proton spectrum free induction decay. And then, mathematically, we get the software to basically perform the Fourier transform. There's lots of software that will do this. We use here a program from Advanced Chemistry Development, and here's a little bit of the screen that does that. Notice there's a button labeled Fourier Transform. You click that, and the free induction decay gets transformed into the actual spectrum. The time domain oscillating function becomes the frequency domain that marks the frequencies of the various peaks. Contained in that information is the fact that some of those frequencies are louder than others. That is where the integration information comes from. It's a remarkably great technique, powerful technique that relies hugely on computer power. NMR was the first form of spectroscopy to make use of it because it had to. There was no way to get the real potential of NMR out without resorting to these advanced techniques here. These days, many of the other forms of spectroscopy, infrared in particular, has gone to working by Fourier Transform instead of directly drawing the spectrum. Even spectrometers like UV-Vis spectrometers are now be sometimes done or purchased with being able to work with Fourier Transform, which enhances their ability even more to detect low concentrations. This is one of our methods we use in NMR to try to overcome the inherent difficulty, the quantum mechanical difficulty in we just have weak signals. There's nothing we can do to change how that, change the quantum mechanics of it, but there are techniques we can use to try to mitigate those problems, and locking, shimming, measuring the FIDs repeatedly, adding them together, and then performing Fourier Transform is the way it's done these days, and that's what's unlocked so much of the power of NMR spectroscopy.